to the Mathematicians Podcast, the podcast where we follow the fascinating stories behind the people that count in the history of mathematics. I'm your host, Benjamin Cornish, and today we'll be taking a very rational approach to mathematical history, Theodorus of Cyrene. I was standing in line at a coffee shop the other day, thinking about how strange it is that we all just agree to stand in lines. Isn't it curious? No one really tells you to do it, and yet there is this unspoken understanding that lines are the right way to handle a crowd. If I'm honest, it's not actually a mystery to me. I'm playing dumb. You might not be able to tell from my accent, but I'm actually British, and we're told about queuing from birth. That and bad-mouthing the manners of other nations. But have you ever noticed how some people, despite the obvious impropriety, start edging forward at an angle, trying to create a sort of personal shortcut? It doesn't make the line move faster, but it's fascinating how human behaviour bends and twists even the most straightforward systems. It's like geometry in action, where straight lines become spirals of intent and impatience. And it's not just coffee shop lines. Think about escalators. There's always that one person who decides that standing still on the right isn't enough for them. They have to walk, no, sprint, up the left side, like they're late for an appointment with destiny. Never mind that we're all headed to the same floor at the same speed, or indeed how an escalator can actually hold a much higher capacity and process more humans per minute if we all stand on both sides of the escalator all the time and no one runs. Or what about boarding gates at airports? That chaotic moment where the airline announces, "We'll now be boarding Group 1, and suddenly people from Group 8 start casually hovering near the gate. It's like they believe their proximity to the line will somehow bend the rules of time and space in their favour. The best, though, has to be theme parks. There's always that one person who's just joining their friends 20 paces ahead of you in line. Oh, sure, their friends are up there waving like this is completely normal and acceptable practice. Meanwhile, the rest of us are stuck calculating how many extra minutes this shortcut is going to add to our wait time. Honestly, if Theodorus were alive today, he'd probably write a whole theorem about the absurd geometries of human queuing behaviour, which no doubt would also be lost to history. Now, what does this have to do with mathematics? Well, geometry has its own way of creating structure and beauty from seemingly small deviations. You might not have heard of Theodorus before, although all of my former students will have, as he is the creator of possibly my favourite work of art. But Theodorus is a critical figure, not just for his mathematical work, but for his place in the intellectual tapestry of his time. He lived around the 5th century BCE in the bustling Greek colony of Cyrene, located in present-day Libya. So let's unwind as we enjoy the life and work of a mathematician who helped prove that some truths lie beyond rationality. Theodorus was a contemporary of other well-known Greek thinkers, such as Socrates. He was an active participant in the intellectual currents of his time. While much of what we know about him comes through references by Plato and later sources, these mentions are enough to paint a picture of his mathematical and philosophical contributions. Cyrene, Theodorus' hometown, was no backwater. It was a thriving hub of culture, trade, and learning, sometimes referred to as the Athens of Africa. It's no surprise, then, that Theodorus flourished here. He was not just a mathematician, but also a teacher of some renown. Plato even mentions him in his dialogues, describing him as a mentor to another notable mathematician, Theaetetus. But Theodorus' fame primarily rests on his work in number theory, particularly in relation to irrational numbers. Before we get into the details of his discoveries, let's take a moment to appreciate what number theory looked like in his era. As you may have noticed, many of our characters so far have been more geometers. To understand Theodorus' work, we need to set the stage. By the 5th century BCE, the Pythagoreans had already made significant strides in number theory. They viewed number as the essence of reality, with their famous motto, "All is number." For the Pythagoreans, numbers weren't just abstract tools. They were deeply tied to philosophy, music, and even the cosmos. However, the Pythagoreans faced a problem, one that may have been a mathematical scandal at the time. While they celebrated the harmony of rational numbers, they stumbled upon something unsettling: irrational numbers. These are numbers that cannot be expressed as the ratio of two integers. The simplest example is the square root of 2, or you might say the diagonal of a square. You have probably encountered a proof before, but how could I resist the opportunity to go over it again? Consider, for a contradiction, the rational value of root 2 is equal to a over b, where a and b are both integers, and also that a and b are the smallest such integers, and of course a is greater than b. In other words, we are assuming that root 2 is a fraction, and we find the simplest fraction that it can be expressed as. So by taking a square of both sides, we are then left with 2 is equal to a squared over b squared, which implies that a squared has to be even, because when divided by b squared it's equal to 2, and if a squared is even, we then have that a is also even. So if a is even, then presumably we can write a as equal to 2k, where k is just another integer, hopefully an odd one, and therefore we could say that 2 is equal to 2k squared over b squared. But by expanding this and rearranging, we might then say that 2 times b squared is equal to 4 times k squared. Both sides can be divided by 2, and we could then divide both sides by k squared, and we're left with b squared over k squared is equal to 2. Now from that we can take the square root, which then leaves us with root 2 is equal to b over k, and k is less than b, so that means we've got an equivalent fraction that a over b is equal to b over k. Since b is less than a and k is less than b, this suggests that we've simplified the fraction. But that's a contradiction to our initial choice of a and b, such that they are the smallest possible values, and therefore this contradiction implies that our original assumption must be false. No such a and b exists. Whoa, slow down there, Ben, I hear you cry. This all sounds very algebraic. Is that what Hippasus did? Sadly, we do not know. The work of Hippasus must have drowned with him, but we can take an educated guess based on ideas that were known at the time. I think this calls for another attempt at me describing a fundamentally visually proof using an exclusively audio medium. Perhaps you can draw along as we go. Let us start by picturing a right isosceles triangle with lengths b, b and a. And naturally a is greater than b, and the ratio a over b is equal to the square root of 2. Assuming for a contradiction that root 2 is rational, we should be able to draw this triangle sufficiently large so that a and b are both whole numbers. We can then also ensure that our triangle is the smallest such triangle that is sufficiently large for a and b to be whole numbers. You might notice this feels awfully similar to the previous proof, and you'd be right. From this triangle, we can measure a point down the hypotenuse that splits it into length b and a minus b. Both will themselves be integer lengths. At this midpoint, we can draw a line perpendicular to the hypotenuse up to one of the lengths of b. Now, this smaller triangle that we have formed will also be right, and because it shares two angles and a side, it must be geometrically similar to the larger triangle. Therefore, it's also isosceles. Thus, the new perpendicular line we drew has length a subtract b as well. Consider the next shape formed in the other part of the triangle. It has two lengths b and two right angles. Therefore, it must be symmetric, a kite in fact. Therefore, we can see in what proportion the perpendicular line has split the other sides of the triangle. The side closer to the original triangle must be a take away b, by the symmetry of the kite, and therefore the other length must be 2b subtract a. Notice that this 2 is a whole number because, of course, a and b are whole numbers. But this smaller triangle, which is similar to the original, will also have a ratio of the sides of the square root of 2. Therefore, the lengths are smaller and all themselves whole numbers, and this contradicts our original statement that we wanted to draw the smallest possible triangle with integer side lengths and a ratio of the square root of 2. Thus, it must be impossible. But can we do this with all irrational numbers? Well, this is where Theodorus enters the scene. Theodorus is most famous for his proof regarding the irrationality of certain square roots. According to ancient accounts, he showed that the square roots of numbers like 3, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15 and 17 are irrational. It's worth noting that he stopped at the square root of 17. Why he chose this cutoff is a mystery that mathematicians still speculate about. To understand what Theodorus did, let's think about the nature of irrational numbers. The key property of these numbers is that they cannot be expressed as a fraction, and their decimal expansion goes on forever without repeating. But how could Theodorus prove this in an era long before decimals or algebra? Well, Theodorus likely used geometric methods, as it was common in Greek mathematics. And while we don't have his original writings, scholars believed he employed something akin to the method of contradiction, similar to the one we saw with Hippasus a moment ago. Essentially, he assumed that these square roots were rational, represented them as a fraction, and then showed this led to a logical impossibility. Perhaps this would be a good exercise for you, dear listener. Can you reconstruct the proof that we mentioned above, but using the square root of 3 as a challenge? What's the highest value that you could do? Now, let's address one of the enduring puzzles of Theodorus' work. Why did he stop at the square root of 17? After all, there are infinitely many irrational square roots, so why not keep going? Some historians argue that Theodorus was constrained by the tools of his time. Geometric constructions became increasingly complex as the numbers involved grew larger. Others suggest that he may have been working within the framework of a specific geometric problem or a teaching exercise, and the cut-off at 17 was simply practical. Maybe he only had an hour's lesson. There's also a more philosophical interpretation. Perhaps Theodorus was demonstrating a method rather than trying to create an exhaustive list. By proving the irrationality of these square roots, he might have aimed to show that the phenomenon of irrationality was not an isolated curiosity, but a pervasive feature of mathematics. Although so far I have not discussed the work of art that I admire so much, this is the spiral of Theodorus. This geometric construction is more than just an artistic curiosity. It's a powerful representation of the interplay between number theory and geometry. So let's unravel the beauty and significance of this spiral step by step. The spiral of Theodorus, also known as the Pythagorean spiral, is created by constructing successive right triangles, each with one leg of length 1 and the other leg equal to the hypotenuse of the previous triangle. Let's break that down. Start with a triangle where both legs are of length 1. By the Pythagorean theorem, the hypotenuse of this triangle is root 2. Next, construct a second triangle using the hypotenuse of the first triangle as one leg, and a new leg of length 1. The hypotenuse of this second triangle would then be the square root of 3. Notice that the square root of 2 squared is 2, 1 squared is 1, 2 plus 1 is 3, take the square root, it's root 3. If we repeat this process, each time creating a new triangle with one leg of length 1 and the other leg equal to the hypotenuse of the previous triangle, we'll then construct the spiral of Theodorus. The hypotenuses of these triangles form the radii of the spiral. As this process continues, the triangles rotate outwards, creating a spiral that expands indefinitely. The spiral of Theodorus is not just an elegant geometric figure. It also embodies several fascinating mathematical properties. Each hypotenuse corresponds to the square root of an integer, starting from the square root of 2. For the nth triangle, the hypotenuse is the square root of n. This geometric construction gives a tangible representation of the progression of square roots. Interestingly, in 1958, mathematician Erich Teufel proved that the segments of the spiral of Theodorus do not overlap up to the 17th triangle, aligning with Theodorus's cutoff point for his work of the square roots. Beyond this, the segments then start to intersect. While the spiral of Theodorus is composed of discrete line segments, as the number of triangles increases, the overall shape begins to approximate a smooth spiral. Not just any smooth spiral, but it tends towards the Archimedean spiral, a topic we shall discuss in a few episodes' time. This highlights the interplay between discrete and continuous mathematics, a theme that would later become central to calculus. My favourite fact about the spiral is that no two hypotenuses are ever collinear, that is, they never overlap. Another fact proven significantly later by E. Hlavka in 1966. The spiral of Theodorus captured the imagination of mathematicians and artists alike in later centuries. It became a subject of study not just for its geometric beauty, but also for its implications in number theory and geometry. The spiral serves as a visual proof of the irrationality of square roots. Each hypotenuse corresponds to square root of n, and the fact that these lengths cannot be expressed as simple fractions for most values of n reinforces Theodorus's critical work on irrational numbers. In modern mathematics, the idea of constructing spirals based on geometric progressions has been extended to higher dimensions. Mathematicians have explored analogous constructions in 3D and even abstract spaces, demonstrating the enduring relevance of Theodorus's ideas. Educators like myself have used the spiral of Theodorus to teach concepts like the Pythagorean theorem, square roots, and irrational numbers. Its visual and intuitive nature makes it an engaging tool for introducing students to these topics. There's just one problem with the spiral. It has no starting point. Or rather, we have no evidence to suggest that Theodorus used the spiral himself as part of his teaching or proof. It's plausible that he was aware of it, given that it is so intimately geometric and fits with the rest of Theodorus's work, but alas, the hypothesis that this was his design comes much later from a mathematician called J. H. Anderhub in 1941. It is simply a suggestion that this is why Theodorus stopped at root 17. Why then include it in today's episode? Well, partly because it's fun, and I don't want to have to wait 2,500 years before discussing it. But moreover, the story of history of maths doesn't need to be factually accurate. Sometimes the story is better than the truth. We are like the ancients themselves, trying to discover our origin story and creation myths. And they too probably knew that the world did not sit on the back of a great turtle, and we know that Pythagoras didn't really discover the triangle, and Archimedes probably didn't run through the street naked. But this is our origin myth. It's the way we look at ourselves. And it's delightful to think that Theodorus doodled in the sand and we are still exploring those implications. Perhaps when we get into later centuries and have surviving written records, I might try to stick more strongly to known truth. Theodorus' work didn't stop at proving irrationality. His contributions were part of a larger effort to rigorously explore the nature of numbers and their relationships. Importantly, his methods influenced his student, Theaetetus, who went on to play a key role in formalising the classification of irrational numbers. Plato's Theaetetus, one of his dialogues of the same name, provides a fascinating glimpse into how this mathematical work intersected with philosophy. In the dialogue, Theodorus appears as a character, engaging in discussions about knowledge, geometry, and mathematical theory. While Plato doesn't go into the technical details of Theodorus' work, his inclusion in this philosophical text highlights the cultural importance of mathematics in classical Greece. Theodorus' influence also extends beyond his immediate circle. His work fed into Euclid's monumental Elements, specifically in Book 10, which deals extensively with irrational magnitudes. While Euclid formalised and expanded on these ideas, Theodorus deserves credit for paving the way. Despite the significance of his work, Theodorus doesn't enjoy the same level of fame as other mathematicians. This may be because his contributions were largely overshadowed by his students, particularly Theaetetus, and by the later systemisation of Greek mathematics in Euclid's Elements. But this doesn't mean Theodorus was forgotten. His work represents a crucial step in the transition from the Pythagorean worldview, which sought to explain everything through rationality, to a more nuanced understanding of numbers and their properties. In many ways, Theodorus exemplifies the spirit of mathematical inquiry, his willingness to confront unsettling truths, to ask hard questions, and to push the boundaries of understanding. His work reminds us that mathematics isn't just about solving problems, it's about exploring the unknown and embracing the complexity of the universe. So, what can we learn from Theodorus? For one, his story highlights the importance of teaching and mentorship in mathematics. As a teacher, Theodorus inspired the next generation of mathematicians, helping to ensure that his discoveries were not just preserved, but expanded upon. His work also serves as a reminder of the power of mathematical proof. Theodorus didn't just stumble upon the irrationality of certain square roots, he demonstrated it rigorously, using the tools available to him. This commitment to proof is fundamental to mathematics, something that continues to shape the field today. Finally, Theodorus' work challenges us to think about the nature of knowledge itself. By proving the existence of irrational numbers, he showed that not all truths are immediately intuitive or easy to grasp. Sometimes understanding requires us to step outside the bounds of our assumption and confront the unexpected. Imagine being the first person to introduce imaginary numbers to a world where people only knew about the real numbers. This transition is similar to expanding on the step of irrational values when all we know are the rationals. Thank you for joining me today on this journey through the life and work of Theodorus of Cyrene. If you enjoyed this episode of the Mathematicians Podcast, don't forget to subscribe and share it with your fellow maths lovers and educators. You can also follow the pod on Instagram at mathematicians.pod for slightly less serious content. Next time, we will be looking in infinitely fine detail at the mathematician and scientist Democritus. It would be pointless to miss it. Until then, goodbye! The music today is Danse Macabre Finale by Kevin MacLeod. You can find more information in the show notes.